So let's start with the geometry node. I'm going to drop down a cube. I'm going to move the cube higher so it's on the plane. So now it's sitting right on the plane, ground plane. And another transformation node. This one is going to squeeze it on the x axis so it's super thin, even more thinner. Okay, so I have a panel. Another transformation node. This one's just going to make it bigger. So I'm going to make it like 5 times as big. And this needs to be a lot thinner. Or maybe 2, 3. Okay, that's good. So I have a basic shape of my glass, a glass panel. Next we're going to use an RBD material fracture. So if you come here, tab, just type RBD, it will list all the RBD tools. Now this set of tools is quite new in Houdini. I think it was first introduced in Houdini 17 or 17.5. I'm not too sure which one. I started using it in 17.5, but as of Houdini 18, sidefx added a lot of new features to the RBD tools. So we're going to check out some of the RBD tools in general and not just the new features in Houdini 18. Now the first one we're going to go over is the RBD material fracture. Okay, so I'm going to hook this up. The material fracture has 4 inputs: geometry, constraint geometry, proxy geometry, and Voronoi points. So the fourth one you should be familiar with. It's like the Voronoi in the Voronoi fracture. Oops, Voronoi fracture node. You would input your geometry here. So I'll just plug it in like that, and then you would scatter a bunch of points, and this would be where you plug in your points. So I could put in our ISO offset. So this might look a lot familiar. Scatter node. So now I have a bunch of points scattered within the volume of my geometry, and these points would go into the second input of the Voronoi fracture. These are the Voronoi cell points. So these points are very similar to this 4th input. There's a lot more to this material fracture. If we look in here, there in the primary fracture tab, there's 1 and 2. There's 2 fractures are happening, and I'm gonna take out the second one. So we're just gonna focus on one fracture, one level of fracturing. It already has a scatter from volume, so this is doing it automatically within the RBD material fracture. It's already doing it automatically. It has the it's doing the ISO offset scatter sort of thing within the node. It's all built in. You can easily change the scatter points to, let's say, 1,000. So we'll have this. Now the reason why it looks different from the Voronoi fracture is because there's a material type fracture. So right now it's fracturing it, treating the fracture as if it was a concrete floor or something. We're going to be using glass a little later. I'm just going to stick with the concrete for now. Fracture, I'm going to go with 0. So I don't want to use the scatter points for the RBD fracture. I want to use my own points. So let's add a point. I'm just going to use 1 point. Let's see. Let's move this up. Okay. Now I'm just going to hook this here to the 4th input of the RBD material fracture. Now nothing's happening. It's not fracturing. That's because we have to, the primary fracture cell points, there's a input point. Now we have to check this in order to enable it. Now still nothing's happening. That's because concrete requires a few more inputs in order to have anything interesting to happen. But I'm going to use glass. Now this is much more interesting. Let me try and template it this way. I'm gonna make the background darker. I'm gonna make the point size 9. So it's not exactly right there. So after you switch it over, the RBD material, let me turn this off. RBD material. I switched it over from concrete, and I already, when it was concrete, I already had this checked. But once you switch it over to glass, the UI changes and the input points are disabled. So I have to check it again. Okay, now it's using it. Now I do not want to use scattered points. So this is additional built-in scattered points on the RBD material. I only want to use my input points. So I want to uncheck this one. There you go. So this is a bit better. Template it like, okay, there you go. So now we can see our point is affecting the way how our glass is fractured. So now we have something interactive. I'm gonna say I want it somewhere in the middle. Yeah, right here. Let's make it in the corner. So now we can take a closer look at this. We can tweak this further. You can see that it has these circle fracturing, like a spider web. We can actually control some of the features of that. Come over to cracks. No, radial crack number. Now this is how many cracks you want, but I want to control the spacing between these circles. Now that's in concentric crack minimum width. Now I'm going to increase this to, now before I increase this, I need more circles first. So making this bigger will only make the width larger within this region, because the noise that defines the concentric cracks is set to this fixed size, already defined as this much. So by making this, if I increase this, this will just make it less circles, because it's limiting how much the width between this larger circle and the smaller circle. However, it's not making more radial cracks. It's not increasing the radial crack area, if that makes sense. Like, I want more cracks. Sort of like, that's where this discontinuity size comes in, is what I'm trying to say. Now I'm going to make this 5. So now I've expanded my concentric crack, is what I'm trying to achieve. However, there's too many lines here. The circles are way too close. So that's where the minimum width comes in. This, I'm going to put it 0.5. So this is a lot better. This is nice. Less. 2.5. Okay, this is pretty good. Now let's come over here. The chipping. I'm not going to be using chipping for this scene. So details, let me disable this noise, edge noise, and you'll see. So now you know what it is. Once you disable it, it's just without the noise, edge noise. It's just straight line. This edge noise makes it way more interesting, like it gives it a more organic feel. Constraints. This applies the glue, but I don't want to apply it here, so I'm going to disable that for now. Now I'm going to throw on a glass material first. I'm going to call this glass. I'm going to start by coming over here. I'm just going to throw in a very quick material. Set up a camera. I'm going to give it a simple dome light. I'm going to turn off the IPR simply because I just want it to render all at once. I'm going to turn off the inplay. Change the camera resolution to 640 to 640. Okay, so we have nothing. I did not attach the material. Okay, I'm gonna turn off the background for the lights. Okay, let's go back to the glass material. Make sure the refraction, the weight, has a value of 1. So this is how it looks rendered out when rendering the RBD material fracture with a very simple glass material. Now the glass material is completely transparent. So we are relying on this dome light to power to light up the scene. The glass material, since it's transparent, there is no color. So it highly relies on light in order to render it out. Now I've increased the intensity of the light, lowered the intensity of the light to 0.3 and exposure to 0.2. There's no HDR map. It's just a plain simple dome light. Let's go back in here. What I wanted to show you is that rendering this glass material like as is not helping, because, well, as you can see, our glass hasn't fractured yet. We haven't even destroyed it yet. So we shouldn't really see these cracks in the render. It should look like a whole, like a whole glass material that is perfect. But when we render this, it's already rendering with all the lines in the middle. Now in RBD, there's something called, come over here, RBD. There's something called RBD faces, connected faces. So let's put this down. Now what this does, this creates a bunch of attributes in the primitives. This is the data that tells it what, records all the data of all of the faces, all the primitives, and gives it an ID. And then it records the distance between the current face and all the nearby face, all the adjacent faces, and then records the distance of it. This does not affect the geometry in any way other than adding more attributes to it. It doesn't change the geometry or anything. What we need to do is add another RBD node called RBD disconnected faces. So we need to use, okay, let's drop this down first. Sorry. We need to connect the geometry output to the RBD disconnected faces. Now what this node does, it uses all the attributes that were created by the RBD connected faces. It uses all these attributes and it will decide what to do with it. Should we create the attribute? But that's not what I really want. I want it to disappear. I want this to help me remove these lines. All my ones, that is a hole, because our glass is a hole right now, and all the pieces nearby each other are right beside each other. So the distance is very minimal. It's rest length. The distance is rest length. If it is rest length, just delete it. So delete the connected faces. And what this will do, it will get rid of all those lines. This node here, RBD connected faces node, stores the distance between the primitives of each piece and neighboring pieces around it. So we get all that prim distance data and record it on the attributes. This node will use it to decide whether to render it or not. And what is actually happening behind the scenes, let's throw down an exploded view. The internal side, inside faces are being deleted. That's what this node does. Now this is handy for rendering simulation. Now we haven't destroyed this glass, so it's not apparent why this is handy, how we'll use this. So let's move this aside. Let's just put them in black, because this was just to show you what it does. Let's come back here. We're going to add the bullet solver. Now I want to mention that the RBD tools now allows us to add the RBD bullet solver onto the SOP level, and we no longer need to drop down a .NET, set up the RBD simulation inside the .NET, and drop down a .import node to extract all the data back up into the SOP level. This new feature of the RBD tools has a way more convenient workflow and saves a lot of setup time. For someone new to Houdini, this will be way more intuitive than trying to understand the .NET and .import nodes. The bullet solver has a lot of inputs. The first one is the geometry. So we know what this is, that's this one. Actually, I should show you. In the RBD material fracture, so the output is geometry, constraint, and proxy geometry. Now let's put a render flag here. This is just the geometry. This is this geometry. Now let's hook this up to the constraint. This gives us a visual representation of the constraints, which are just primitives. Very much like the Vellum workflow. The constraints are primitive. They're edges. They're actual geometry representing the constraints. Now, if we put this to the proxy geometry, it will be, this is a low poly version of the high quality geometry. Now, as you can see, the difference between, let me turn on the points. Let me make the point size a little lower. So you can see, I hope you can see, these points are jaggedy. They have a lot of noise. They have a lot of detail on them. The low quality one, there's a lot less points. Now, why would we need a lower quality version of this? Because using the low quality, low poly version, the proxy geometry, for this RBD simulation, it will be more cost efficient to the simulation. Plugging this high quality geometry into the simulation does not benefit us, and in fact it makes the simulation a lot slower because there's more points to process. The lower quality version is very close representation of the high quality one without the cost long cooking times. This is a performance saving technique that the RBD tools use within its workflow. However, this isn't new in Houdini. Proxy geometry has always been used in simulations. In a previous video of mine where I demonstrate how to set up flip simulations and how to deal with complex collisions, I use a proxy geometry to help improve the accuracy of the simulation. Now the RBD bullet solver. There is the geometry, the constraint geometry, proxy geometry, collision geometry. If you have an animation, which we're going to add a really simple animation that will knock part of this solver to destroy maybe a ball hitting at this wall. This is where you would put it. Plug it in here. The fifth plug would be the guide simulation, which will be discussed in a different video because that's a little bit more complex. It's basically external forces that will influence the simulation and how it breaks. Now let's plug in what we know. Let's plug in the geometry, the constraints, proxy geometry. Now if we just run it as is, it just falls down because there's nothing to collide with. Let's add a ground. So in the RBD bullet solver, bullet object, collisions, ground. So this is where we put the ground. Put the ground plane. It's right there. Now in forces, it already comes with gravity. So that's very handy. So we can just play it right now. Oh. Let's take a look at this error that we're getting. I do not have constraints. I did not define constraints because in the RBD material fracture constraints, I turned this off. So I wanted to define it a little later. The problem is this RBD bullet solver, when you come to solver, constraints, breaking thresholds, it's trying to find something to break. It's trying to find a constraint to break. And it's trying to find these constraints, which I have not, so it's not working properly. Now, let's define some constraints. RBD constraints. There's a few ways you can define it. This is the most simplest way. It's actually the exact same way as the RBD material fracture is set up. The UI is almost identical. You can convert curves, so you can manually put down curves to drive the RBD constraints. You can put lines, you can have rules, but I'm going to use a simple version of the RBD constraint properties. I'm going to throw this down. Hook this here. So this RBD constraint, now this UI will look very similar to what we had here, to this part of the UI. It's almost identical. So I'm going to put it here. You can define it here. You can just check this and just define it here if you wish. I just want to show you a different way of doing it. RBD constraint properties here, glue. Now this is 10,000. This is way too much. I'm just gonna lower this 1,000. Now I want to see my constraints. We can actually color. So I'm gonna give it. Come over here. Press W to go into wireframe mode, and you'll see your constraints because it's inside the geometry. Now let's retry the RBD solver. Let's replay it. Take a look what the render looks like. Let's pick a different frame. Now if you look carefully, this part is not shattered. This part, we can see that it's shattered. So we can see that this part, which is this part, is shattered. Now this middle part is intact. This spider web, the origin of the spider web is intact, but we're still rendering the crack. That's not very useful because it looks like it's already cracked before it's even collided with anything, before it's even broken. So the idea is to use this RBD connected faces and RBD disconnected faces to delete the connected ones, to delete the geometry, these lines, the interior lines, so they don't render but we want to render them when they are actually broken. Like for these pieces over here, we want this to stay. Now that's how we're going to use this RBD connected faces and RBD disconnected. Now what the RBD connected faces does, this only creates these attributes. It doesn't change the geometry. Now we want to create the attributes. Oh, actually, sorry. I should keep this here. I should create a copy of this because I'm going to release this file out. So I want you to have this for reference. So I want you to have this side for reference. I'm just going to stick it here. This doesn't have to be black anymore. So this, let's give it red actually. This is RBD connected faces, only creates these primitive attributes. What it does tell us is how close they are. This is sort of like the rest length, how close they're supposed to be. And when we put this down, so after this, the solver, the RBD bullet solver does not change these primitives. So the RBD bullet solver, let's go to the primitives, primdist. This list should not change. Let's check out, okay, face ID 2325. It's 0.0324683. Let's go to a different frame. Face ID 2325. Primdist 0.0324683. Face ID. So it hasn't changed. Throughout the whole timeline, this prim distance is not changing. It's sort of like the rest length. What is the original resting position? So we know what's the distance between each piece before the glass is broken, when it's a perfect glass. Now we can throw on the RBD disconnected faces. So this is what we need here. And we're going to connect this to the geometry. Change the color to red. By using it this here, we're going to delete the connected pieces. So we're going to delete these lines. These lines are going to go away in the render view if they are not broken. So the ones like these ones, this one here, let's take a better frame. Okay, these ones here, they're actually broken. They're disconnected. So then we want to keep those faces. So let's put the render flag here. Now let's go to the render view. Hit this. This has disappeared. Now you still see it in the 3D viewport because this is the outside view. Now you don't see it in the render view. So this is the 3D viewport. It's both the same frames, frame 75. Now these pieces here, the key is these pieces. These fractured pieces, they still have the face, they still have their a face here. Go back here, go here, and I'm going to show you something. And I'm going to show you that it's actually disconnected. It's deleted. The interior pieces, the interior primitives are deleted. What let's do is add an exploded view. Yeah, this is probably easier. I'm going to explode it very little. So this is non-exploded. So everything's intact. So this part is rendering. Now this part, I want to show you that these parts, that this larger piece that's intact does not have interior sides. So I'm going to slowly increase this. Okay, so we can already see this. So this is separated islands. There is no interior sides to this, which allows the rendering to give it this solid piece look, because there's nothing in the middle that's refracting the light. That is how you use RBD connected faces. So this is only for debug purposes. I'm gonna move this down. Now I'm gonna add an RBD IO. So RBD Tools comes with its own file caching. This is identical to the file caching that we normally see like this. This is identical to that, except because RBD Tools has multiple inputs and multiple outputs, this RBD IO is very handy because all you have to do is hook these up in the correct order. Geometry, constraints, proxy geometry, and simulation points. So it goes in the same order as this one. Hook this up, and this UI should look very familiar to you, except for this is the only difference between the file cache, the normal regular file cache, and the RBD IO. This will store everything. Pack geometry, constraints, proxy, everything. This will only store the geometry. Maybe you want to save yourself a few megabytes. So you just want to store this. You only want to file cache the high quality geometry. Then you can select this. This will record the geometry and the simulation points. I would prefer, if you're going to file cache it, because the constraints in the proxy, it's not as big. It's not as that big. I mean, it's rather than recooking everything, recooking the whole simulation. So I would always use the middle one. Check the load from disk. I usually take out the HIP name only because I have multiple HIP files. So this makes it easier for me to swap HIP files. Now, be aware that this RBD IO is very similar. So I'm going to connect this to the RBD disconnected faces first. So after you save it, so you want to save all the simulation data here and then attach the RBD disconnected faces here. Because removing faces, like all this is doing is delete connected. This is just deleting stuff. Deleting stuff is very quick to do. If you put the RBD IO after the RBD disconnected faces here, now this you lose a lot of data. You lose all the constraints. You lose the simulation points and proxy geometry. So you lose a lot of data. You're gonna if you have anything else might think of something you want to change the simulation on, like add an attribute wrangle after this, then you'll have to recook it because you don't have the constraint information. So modifying anything else would make it a little more difficult. So that's why the advantage of putting this node, let's disconnect this node up here. No, I'm just gonna delete this. RBD IO. Hover the mouse over here to get it all connected. And you can connect this if you want. Connect this over here. And again, I like to delete this. Check this, and you can hit the save to disk button. Now, this RBD IO is like having 4 file caches. But it's just hooked up to the geometry, constraint, proxy, and simulation points. So this one RBD IO node is like equivalent to having 4 file caches. The functionality is very similar. The RBD connected faces and RBD disconnected faces nodes are extremely handy for rendering transparent materials, but I also think this would be handy for 3D printing. 3D printers use applications like slicers to digitally slice the model into hundreds of horizontal layers that the 3D printer will then print each layer one at a time. If we use both RBD face nodes to delete the interior faces, it will create a more smoother model ready to be 3D printed. As a bonus, the slicer would be able to parse the file more quickly as well, because there are less polygons. You could always use a Boolean node instead to weld all the pieces together, but sometimes if you have a lot of fractured pieces, the Boolean node could take a while. Using both RBD face nodes, you can quickly and easily remove the interior primitives and save it as a STL file that's ready to be 3D printed. Thank you for watching and sticking to the end.